Imagine cooling a gas to temperatures colder than anything found naturally in the universe. As you chill the gas, its atoms slow down, moving sluggishly like tired dancers at a party. Now imagine cooling the gas even further, to just a hair above absolute zero, the point at which all motion stops entirely. The atoms, once distinct entities, begin to overlap, losing their individual identities and behaving like a single unified wave. This strange state of matter is called a Bose-Einstein Condensate, or BC. First predicted by Satyendra Bose and Albert Einstein in the 1920s, BCs weren't observed until 1995, a testament to the challenges of reaching such extreme temperatures. By manipulating the properties of BCs, researchers can explore phenomena such as superfluidity, where matter flows without any resistance, and atom lasers, which emit beams of coherent atoms analogous to the light from a laser. The key to creating a BEC lies in reaching ultra-low temperatures, just billionths of a degree above absolute zero, which is minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit. At these frigid temperatures, the thermal energy of the atoms, which normally causes them to jiggle and move around randomly, is almost completely extinguished. As the atoms slow down, their quantum mechanical wave-like nature, usually hidden by their frenetic motion, begins to dominate. Imagine each atom as a tiny wave, spreading out over a region of space. The first BECs were created using clouds of rubidium atoms trapped and cooled using lasers and magnetic fields. Since then, BECs have been created using a variety of other atoms, including sodium, lithium, and potassium, each with its own unique properties and potential applications. A light, too, exhibits wave-particle duality, behaving as both a wave and a particle, which we call a photon. However, creating a BC of light, also known as a photon Beck, poses unique challenges. Unlike atoms, which have mass and interact with each other, photons are massless and typically pass through one another without interacting. This makes it difficult to cool and trap photons in the same way as atoms. Furthermore, the number of photons in a system is not necessarily conserved, as they can be created and destroyed through various processes. Therefore, achieving BEC in a photon gas requires overcoming these challenges by finding ways to effectively cool and trap photons while ensuring number-conserving thermalization. Section 4. Trapping light. To overcome these challenges and create a photon Beck, scientists have turned to optical microcavities. These devices, consisting of two highly reflective mirrors facing each other, can trap light for extended periods, allowing it to interact with its surroundings and potentially reach thermal equilibrium. Inside the microcavity, photons bounce back and forth between the mirrors, effectively increasing the density of the light. By carefully choosing the materials and geometry of the microcavity, scientists can control the way light interacts with its environment, promoting thermalization and enhancing the conditions for BC formation. For example, one approach involves introducing a dye solution into the microcavity. The dye molecules can absorb and re-emit photons, effectively mediating interactions between the photons without altering their number. Section 5. A glimmer of the future. The experimental realization of a photon BC in an optical microcavity marks a significant milestone in the study of quantum many-body systems. By demonstrating that BEC is not limited to atoms and can also occur in bosonic gases of light, this discovery opens up new avenues for exploring the fundamental nature of BEC and its potential applications. One exciting prospect is the development of novel light sources with unprecedented coherence and brightness. Just as atom lasers utilize the coherence of BECs to generate beams of coherent atoms, photon Becks could lead to the creation of ultra-bright and coherent light sources with applications in various fields, such as high-resolution imaging, sensing, and quantum information processing. As researchers continue to explore the properties and potential applications of this novel state of matter, we can expect further breakthroughs that deepen our understanding of the quantum world and its profound implications for science and technology.